In quantum mechanics, a pure state represents a system with total predictability. If you know the exact pure state, you possess maximal information about that system. Imagine taking the complete quantum description of a massive star and allowing it to undergo total gravitational collapse. According to semi-classical physics, the resulting black hole eventually evaporates completely, but the outcome is not a pure state. Instead, it leaves only a diffuse, featureless thermal haze, the state described as a mixed density matrix. This result challenges the unitary time evolution required by quantum theory. Unitarity is a conservation law for probability. It mandates that a pure state must always evolve into another pure state, ensuring the process remains reversible in principle. Stephen Hawking's calculations showed that the radiation emitted by a black hole is determined only by its macroscopic properties. Because the radiation is approximately thermal, it retains no memory of the specific initial state of the star. This creates a direct contradiction. In a unitary universe, every distinct input must lead to a distinct output. In Hawking's model, millions of different starting configurations emerge as the same output, making it impossible to reconstruct the past. The mathematical conflict remains even after accounting for subtle environmental factors. It is an unavoidable result of treating quantum fields as if they exist on a classical gravitational background. If this transition from a pure state to a mixed state is real, then unitary evolution is broken. The fundamental symmetry that allows quantum mechanics to remain a consistent, predictable theory would no longer be universal. To isolate where this conflict begins, we have to look at how general relativity describes a collapsing star. The event horizon defines the black hole as a global causal boundary. It is the point of no return, the mathematical line where the interior is permanently separated from the future of the outside universe. This global boundary is distinct from local apparent horizons. An apparent horizon marks the specific region where gravity becomes so intense that even light rays attempting to move outward are dragged backward. Within these regions, the geometry of space-time creates trapped surfaces. On these surfaces, every possible path leads further inward toward the center. Roger Penrose used the existence of these trapped surfaces to formulate his singularity theorem. Penrose proved that trapped surfaces lead to geodesic incompleteness. Paths through space and time simply terminate, suggesting that the classical description of the universe ends at a central singularity. While the interior is marked by this abrupt termination, the exterior geometry settling into a perfectly stable, stationary state. This process is governed by the no-hair theorem. As the black hole stabilizes, the exterior retains only three measurable values: mass, angular momentum, and charge. Millions of microscopic variables from the original star are effectively locked behind the horizon, becoming invisible to the universe. Classical black holes create a state of perfect causal isolation. Information can enter, but the geometry prevents any possible exit, even as the equations themselves fail to describe the singularity at the center. The model changed when Jacob Bekenstein realized that black holes must obey the laws of thermodynamics. Bekenstein argued that a black hole possesses entropy, but unlike ordinary objects, its entropy is proportional to its surface area rather than its volume. This area law preserves the second law of thermodynamics. It ensures that even when matter disappears into a black hole, the total entropy of the system never decreases. Stephen Hawking later proved that this entropy is physical by showing that quantum fields in curved space emit thermal radiation. We visualize this as pair production at the event horizon. Vacuum fluctuations spawn particles in pairs. One escapes as Hawking radiation, the other falls in. Created together, a quantum entanglement link connects the interior partner to the escaping radiation. Because the interior is causally disconnected, an external observer has no access to the infalling particle. To measure radiation, they mathematically ignore the interior, tracing out hidden degrees of freedom. This breaks the link, transforming the escaping radiation into a fuzzy thermal state. Combining a smooth horizon with quantum field theory, the act of ignoring the interior partners makes information loss an inevitable feature of black hole evaporation. To understand why this is a paradox, we have to look at evaporation through the lens of quantum information science. In this framework, the black hole is a quantum channel, a map that takes the information of collapsing matter and encodes it into outgoing radiation. This differs significantly from standard decoherence, such as heat dissipating from a cooling engine. In standard decoherence, information leaks into the surrounding environment, but the global state of the universe remains pure and potentially recoverable. But if a black hole evaporates completely and the interior vanishes, there is no environment left to hold those correlations. The global state of the universe itself changes from pure to mixed. This conflict is defined by the monogamy of entanglement. If an observer is to see a smooth, empty horizon as relativity predicts, a late particle of Hawking radiation must be maximally entangled with its partner inside the hole. However, if information is preserved through unitarity, that same late particle must also be maximally entangled with the early radiation. A quantum system cannot be maximally entangled with two independent systems at the same time. To satisfy both requirements, the particle's quantum information would have to exist in two places at once. But the no-cloning theorem makes this impossible. It is physically forbidden to create an identical copy of an arbitrary, unknown quantum state. These strictures prove that smooth horizons, independent interior and exterior systems, and unitary evolution simply cannot all coexist simultaneously in our current framework. Don Page developed an entropy diagnostic that translates this entire theoretical clash into a single graph. This chart tracks von Neumann entropy over time. The semi-classical calculation of an evaporating black hole produces a line that moves steadily upward. This is the Hawking curve. This upward path represents the continuous growth of entanglement between the radiation and the hole, right up until the evaporation terminates at its highest point, leaving behind a mixed state. If information is preserved, the entropy must follow a different trajectory. At roughly the halfway point of evaporation, we reach an inflection point called the Page time. Beyond this point, the early radiation begins to purify the late radiation. The entropy drops back to zero, returning the universe to a pure state once the black hole is gone. The Page curve is not a physical mechanism, but a mathematical requirement. Any valid theory of quantum gravity must produce this result. Achieving this curve requires a sacrifice from our conflicting assumptions: unitary evolution, semi-classical theory, locality, smooth horizons, independent subsystems, and the absence of remnants. The question remains, which of these assumptions is wrong? To preserve the unitary evolution of quantum mechanics, we must eventually reject either the smoothness of the horizon, the independence of the black hole interior, or our understanding of the fabric of space-time itself. For 50 years, the black hole information paradox centered on Stephen Hawking's original calculation that black holes destroy information. Today, however, the field is organized around a different expectation, that information is preserved. To test this assumption, we use a diagnostic established by Don Page. If black hole evaporation is a unitary quantum process, meaning no information is lost, this trajectory maps entropy over time. Hawking's math produces a rising curve ending at a peak, indicating a mixed state with erased data. For a unitary process, after the Page time, radiation purifies. The curve drops to zero as a mathematical diagnostic. Any viable theory of quantum gravity must provide a specific calculational method explicitly reproducing this exact downward trajectory. We can distinguish between two ways of observing Hawking radiation. A coarse-grained view sees only a featureless thermal field, but a fine-grained measurement examines the exact quantum correlations between the individual particles being emitted. While the radiation looks random at a macroscopic level, the specific state of the collapsed star is deterministically encoded inside those fine-grained correlations. To explain how this encoding occurs, physicists Patrick Hayden and John Preskill modeled the black hole as an optimal quantum scrambler. When information enters a black hole, it does not disappear. It mixes into the internal degrees of freedom at the maximum speed permitted by quantum mechanics. This mixing occurs on the scrambling time, diffusing information across the entire system almost instantly. Because the dynamics are unitary, the scrambled information can eventually re-emerge in the late-stage radiation. An observer could theoretically decode it, provided they have collected the early radiation and have the computational power to process it. By treating black holes as efficient encoders, The focus of the paradox shifts. We are no longer asking if information survives, but how semi-classical geometry can track this highly scrambled recovery. The challenge is to find a rigorous method within semi-classical gravity that forces the radiation's entropy curve to bend downward. This diagram maps the evaporation's causal structure. We focus on distant radiation region R. To compute its entropy, we use the generalized entropy functional, combining two inputs: the geometric area of the boundary surfaces, and the bulk quantum entanglement entropy of the fields between them. To find the true entropy of the distant radiation, we must extreminize and minimize this generalized entropy across possible boundaries, identifying quantum extremal surfaces. The structure of this formula creates a specific tension. It suggests that the relationship between the black hole's interior and the radiation escaping it may be more complex than a simple classical boundary. Early in evaporation, the generalized entropy calculation is straightforward. The radiation's entanglement wedge is bounded strictly outside the event horizon. Accounting only for exterior degrees of freedom, the radiation's entropy steadily increases, mirroring the initial upward slope of Hawking's original curve. Exactly at the page time, a geometric phase transition occurs. A new quantum extremal surface becomes dominant, revealing an island, a disconnected region deep inside the black hole. The math implies this interior region now belongs directly to the distant radiation's entanglement wedge. Therefore, the late-time radiation's entropy isn't measured by the exterior alone, but by the union of the radiation and this interior island. Evaluating them together with the internal Hawking partners purifies the state, and the combined entropy necessarily drops. By carefully following the geometric rules of quantum extremal surfaces, the calculations automatically reproduce the unitary page curve. The island formula tracks the entropy, but its mathematical justification lies in the gravitational path integral. To analyze this, physicists use the replica trick. This involves taking multiple identical copies of the black hole and its surrounding geometry and evaluating them as a single system. When calculating the sum of all possible geometries in the path integral, new mathematical configurations emerge. These configurations are called replica wormholes. They act as topological links, connecting the interiors of the different replicated manifolds. These replica wormholes are Euclidean saddle geometries. They are mathematical tools for entropy accounting, not physical traversable tunnels that carry matter out of the black hole. At the topological level, these configurations are the structures that shift the entropy result away from Hawking's rising line and onto the unitary page curve. 50 years after the paradox was first identified, these entropy formulas have successfully reconciled the original Hawking problem with the requirements of quantum mechanics. These calculations prove that semi-classical gravity, when used with the correct geometric entropy rules, is inherently compatible with unitary evaporation. However, there are significant limits to these results. These proofs rely on strictly controlled lower-dimensional toy models coupled to non-gravitating thermal baths. It remains difficult to map that mathematical precision directly onto the complex four-dimensional astrophysical black holes observed in our universe. Furthermore, while the island formula correctly tallies the entropy, it does not identify the exact microscopic degrees of freedom that carry the information outward. These models also do not provide a protocol for an external observer to decode the radiation, nor do they resolve what an infalling observer experiences at the horizon. Islands and replica wormholes have successfully answered how to compute the preservation of information, but the search for the microscopic quantum narrative of spacetime remains an active frontier. Is the black hole interior a physically independent place hidden behind an event horizon? Or is inside simply an encoded representation of the outside? Classical physics dictates that the maximum information capacity of a region, its maximum entropy, scales with its volume. To store more quantum states, you need a larger physical container. This animation models the Bekenstein-Hawking area law, upending that expectation. The equation dictates a black hole's maximum entropy scales with surface area, not volume. Because of this geometric constraint, local quantum field theories using volume-based cutoffs vastly overcount the true gravitational degrees of freedom. Stephen Hawking's original calculations from the 1970s treated quantum fields on a fixed classical volume of spacetime. Because he assumed this classical structure, He concluded that any information falling past the event horizon is permanently lost when the black hole evaporates. Treating the interior volume as an independent container of information is mathematically incorrect. The true capacity of spacetime is dictated entirely by its boundaries. The ADS-CFT correspondence provides physics' most rigorous proof of information preservation. A 2D theory on the outer boundary projects a 3D gravity interior. These domains are exact duals. Internal 3D gravitational dynamics are strictly equivalent to the ordinary quantum mechanics on the 2D boundary. The boundary theory is strictly unitary, evolving through perfectly reversible quantum mechanics. Information cannot be destroyed. If a black hole forms inside and emits Hawking radiation, the boundary tracks the entire process with matrix equations representing exact unitarity. Because the boundary dictates the bulk, and the boundary cannot destroy information, black hole evaporation inside the bulk must also be entirely unitary. If information survives evaporation, the black hole interior cannot exist as an isolated location. It is an encoded hologram playing out on the boundary. How exactly does a single interior particle get completely projected onto a lower dimensional boundary, or entirely into distant radiation? This animated cross-section of the ADS cylinder demonstrates the concept of entanglement wedges. A specific boundary region, labeled R, projects a wedge deep into the bulk, capturing an interior region known as an island. A specific subregion of the boundary, or a collection of Hawking radiation, can mathematically reconstruct specific regions of the deep interior. The mechanical process for this reconstruction is holographic quantum error correction. Interior data is not stored in a single localized safe. Instead, the tensor network shows how the data is redundantly smeared across exterior degrees of freedom. The single central node represents the logical qubit of the interior. It connects via multiple complex tensor pathways to the perimeter nodes, which act as the physical qubits. This redundant encoding does not violate the quantum no-cloning theorem. The inside and the outside are not independent copies. They are two different mathematical representations of the exact same logical subspace. The interior of a black hole is an emergent property, constructed directly from the complex entanglement of the exterior. To stress test whether the interior and exterior can truly be treated as independent places, physicists rely on the AMPS paradox. This Penrose diagram maps an evaporating black hole using three specific quantum wave packets. V is late radiation just outside the horizon, A is its interior partner, and R is a vast cloud of early radiation far away. To maintain a smooth horizon and satisfy the equivalence principle, mode B must be maximally entangled with mode A. To preserve unitarity and follow the page curve, mode B must simultaneously be maximally entangled with the distant radiation R. Quantum mechanics enforces the monogamy of entanglement. A single quantum system cannot be maximally entangled with two independent systems at the exact same time. If we assume A, B, and R are completely independent subsystems, we hit an unresolvable mathematical conflict. The bluntest resolution to this math problem is the firewall. Breaking the entanglement between A and B to save quantum mechanics destroys the vacuum state, creating a wall of high-energy radiation at the event horizon. Forcing classical notions of independent locality onto black holes requires breaking the equivalence principle and setting the horizon on fire. The primary physical argument against literal firewalls is that for supermassive black holes, the horizon is a region of incredibly weak curvature. Infalling observers should cross it without experiencing any drama. So how is the AMPS contradiction dissolved without a firewall? This diagram exposes a mathematical flaw: naive tensor factorization. Physicists modeled the universe as a clean split, the inside tensored with the outside. But through ER equals EPR and entanglement wedges, gravity forbids this. Node A is actually a scrambled subcomponent of the distant cloud R. A and R are not independent Hilbert spaces. The interior is encoded within the exterior, dissolving the monogamy of entanglement conflict. The paradox is a failure of our assumption that different regions of space are fundamentally independent of one another. Resolving the paradox without firewalls exacts a profound conceptual price: emergent locality. Spacetime and locality are excellent, highly successful, effective descriptions for low-energy observers, but they are not the fundamental basement of reality. Quantum gravity requires a dual reality. The interior is a physically real experience for the infalling observer. To a distant observer, that exact same interior experience is encoded redundantly in the exterior radiation. These are not physical copies. They are complementary descriptions of a single underlying quantum state. Gravity forces us to abandon the idea of isolated places in the universe. Space-time itself is merely a localized illusion woven from distant quantum information.
In classical general relativity, a black hole is the ultimate one-way street. Once matter crosses the threshold of the event horizon, its trajectory is locked. It falls inward, and it never returns. Stephen Hawking used this exact classical framework in the 1970s to uncover a massive contradiction. He based his math on two strict rules from Einstein's theory. The horizon is an empty vacuum, and at the very center sits a point of infinite density called a singularity. Because that horizon is completely empty space, quantum pairs created there are ripped apart cleanly. One particle escapes as radiation, while its partner falls into the singularity. Over billions of years, the black hole completely evaporates into this featureless radiation. The inward partners, and all the information they carry about the star that originally collapsed, are permanently erased from the universe. That erasure directly violates the laws of quantum mechanics.
So if we want to save quantum theory, tweaking the math of the escaping radiation isn't enough. We have to consider throwing out the classical model of the black hole altogether. This leads us to a strategy among many physicists: horizon denial. Instead of treating the boundary of a black hole as empty space, this approach replaces the horizon with a physical, complex quantum structure. Adding a physical surface prevents the inward partner from disappearing into an abyss. The particle hits this dense structure, interacts with it, and bounces its data back out into the escaping radiation. It solves the information paradox locally. But the cost is steep. To make this math work, physicists have to invent unproven states of matter or radical spacetime geometries that we have never observed. The most rigorous attempt to build one of these physical horizons comes from string theory, with a concept known as the fuzzball. In this model, you don't have an empty void leading to a singularity. Instead, the geometry of spacetime physically caps off. The black hole is modeled as a dense, vibrating ball of fundamental strings and branes that reaches all the way to the edge of where the horizon would normally be. Because the fuzzball has a physical surface, radiation isn't born from an empty vacuum. It emits directly from the vibrating string structure, exactly like heat radiating off a warm piece of coal. The escaping energy carries all the fine-grained data of the object with it. The math here is precise, but only under very specific conditions. The exact fuzzball models we can construct rely on highly symmetric, specialized versions of gravity. They do not yet accurately describe the messy, spinning black holes we actually see in our own night sky. Another major family of theories tackles the problem by focusing on the core, using loop quantum gravity to create Planck stars and quantum bounces. Loop quantum gravity treats space-time itself as discrete and pixelated. When a dying star collapses, it can't crush down to infinite density. It hits a physical limit, the Planck density. At that threshold, quantum pressure halts the collapse, and the entire structure rebounds outward into an expanding white hole. There is no singularity. The information falls in, gets heavily compressed during the bounce, and then flows back into the universe as the geometry expands. The problem is time. To an outside observer, intense gravity warps the clock. A bounce that takes milliseconds at the core might appear to take trillions of years from Earth. Plus, we still lack the full mathematical derivation to prove this works in standard four-dimensional space. If you want to avoid unproven quantum gravity altogether, you can look at phenomenological models. These are horizonless compact objects, like gravastars and boson stars. These theories replace the black hole with macroscopic fields or dense vacuum condensates.
They form physical shells that sit infinitesimally close to where the light gets trapped, the photon sphere. This image from the Event Horizon Telescope shows the specific shadow profile and glowing photon ring of an active galactic core. Because a gravastar or boson star is so compact, it bends light in almost the exact same way, mimicking this visual profile without possessing a true horizon.
But building a convincing mimicker comes with a catch. To keep these objects from collapsing under their own weight, you have to pack them with exotic faces of matter, like dark energy cores. And as our gravitational wave detectors get more sensitive, they are struggling to pass tests looking for echoes bouncing off those physical surfaces. Finally, we reach a category of theories that allow the horizon to form, but propose that evaporation stops before the hole vanishes entirely. These are remnants. Here, the black hole evaporates until it shrinks down to the microscopic Planck scale. Then the evaporation simply stops. It leaves behind a tiny, stable nugget that traps all the original information inside. The trade-off here is storage capacity. You're taking the entire quantum history of a collapsed star and cramming it into a space smaller than a proton. In standard physics, packing large amounts of data into a finite microscopic volume triggers feedback loops, like runaway particle production. Another fringe concept abandons our geometry entirely: baby universes. Under extreme pressure, the singularity pinches off from our spacetime and creates a disconnected branch. The information flows out of our universe and into this new one. On a multiverse spreadsheet, no data is technically destroyed, but if that data is sealed inside a baby universe, we can never reach it. If information is permanently inaccessible to our native universe, then operationally, it means the information is destroyed. With so many competing models, physicists have to pick which theoretical compromises they are willing to accept. This matrix charts out the major theoretical camps. If you prioritize strict mathematical consistency at the smallest scales, the ultraviolet completion of gravity, you land in the string theory camp. Fuzzballs check the box for deep quantum gravity, even though they currently fail the test of describing observable black holes. Researchers choose this path because they prioritize fundamental quantum constraints over current maps of astrophysics. Conversely, if you prioritize objects that can form from dying stars and produce the gravitational wave signals we detect today, you lean toward phenomenological models. Mimickers and bounces give you practical astrophysical objects, but they require you to accept incomplete quantum math. There is no perfect answer yet. A researcher's choice of model is dictated by which rule of classical physics they are most willing to modify. Luckily, we are no longer relying entirely on chalkboard math. Observational data is finally beginning to physically constrain these alternatives. Facilities like LIGO analyze the exact ringing frequencies of colliding black holes. Those searches strictly limit the viability of horizonless mimickers, because a hard, reflective surface near the horizon would produce distinct gravitational echoes that we simply haven't found yet in the data. Right now, none of the alternatives we've discussed hold universal consensus among the physics community. These models act as conceptual diagnostics, helping researchers pinpoint the specific gaps in the semi-classical framework. Whether the horizon is an empty vacuum or a physical shell is still an open debate. These theories show saving quantum mechanics requires us to modify a piece of classical gravity. The mystery is which one we'll have to give up. We point telescopes at black holes and watch them devour matter, but we still lack a working description of what happens at the microscopic level. The physics break down exactly where the black hole begins. The Event Horizon Telescope gave us our first direct look at this boundary, capturing the ring-like emission and the dark central depression of the supermassive black holes in M87 and our own galaxy. This split-screen visual shows what those images accomplish. They set strict limits on large-scale deviations, ruling out massive, solid surfaces far from the center. But they do not have the resolution to see Planck-scale quantum structures right at the horizon. On the gravitational wave side, the in-spiral, merger, and ring-down signals we record match standard general relativity. They behave as the math predicts a rotating Kerr black hole should behave. The observational data confirms that these massive, dense objects exist. But it leaves the microscopic fate of the actual event horizon completely hidden, handing the problem over to quantum gravity. To test if there is physical structure at the edge of a black hole, researchers scan gravitational wave data for late-time echoes, signals bouncing off a hard boundary. This quadrant chart maps the current state of those searches. We plot proximity to the horizon on the y-axis against the strictness of our constraints on the x-axis. Our best data points are clustered far away from the horizon, and the lack of robust echo detections restricts models that require a hard, reflective surface. Notice the origin point. Telescopes cannot mathematically prove the existence of an infinitely sharp event horizon or a central singularity. That scale remains empty. Because our instruments hit a hard resolution wall, resolving the paradox requires taking physics apart on paper. Resolving this problem involves a direct trade-off. To make quantum mechanics and gravity compatible, theorists must choose which core principle to abandon. Stephen Hawking laid out the original calculation that triggered the paradox, proving a mechanism for black holes to slowly evaporate through thermal radiation. This matrix compares theoretical options. Row 1 tracks Hawking's math. It provides evaporation, but information is permanently lost, breaking quantum mechanics. Row 2 introduces the firewall solution. It saves quantum mechanics by placing a wall of high-energy particles at the horizon. The trade-off here is the equivalence principle. Instead of an astronaut floating smoothly across the boundary, they would immediately burn up, turning the horizon into a violent physical barrier. These initial theoretical attempts to save quantum information resulted in a breakdown of the smooth spacetime Einstein predicted. This diagram illustrates a different approach. The string-theoretic fuzzball model replaces the empty interior with a dense structure of quantum microstates, removing the central singularity entirely. Returning to the matrix, fuzzballs protect quantum information but sacrifice the empty vacuum. Row 4 adds loop quantum gravity bounces. In these models, gravity repels at extreme densities, forcing collapsing matter to bounce outward like a white hole. This method replaces the permanent event horizon with a temporary one. The matter slows down drastically due to relativity, but the exact timescale for when it would bounce back out depends entirely on the specific model. Replacing the empty void with complex structures can solve the math, but it requires moving away from the standard astrophysical picture of a black hole. The fifth row introduces the remnant hypothesis. Here, evaporation stops at the Planck scale, leaving behind a microscopic object that stores the original data. But storing an entire star's worth of data in an object that's small presents a problem. It requires an almost infinite number of internal states, which usually leads to massive instabilities in particle physics. Row 6 introduces baby universes, where information passes into a disconnected spacetime, keeping math pure, but lost to our universe. Finally, row 7 shows holography and islands. It recovers the entropy curve by treating the black hole interior as part of the radiation. This is currently the most supported framework in the field, but it demands that we abandon the idea that inside and outside the black hole are independent, separate locations. This flowchart tracks where the progress is actually happening. By using these mathematical islands, we finally have a way to account for all the entropy as a black hole evaporates. Because this accounting balances the ledger, it provides the most concrete evidence we have that information is not actually destroyed. But notice the bottleneck. These calculations rely on lower-dimensional toy models. We don't yet know how to translate these holographic lessons into the four-dimensional universe we actually live in. We have a mathematical path that shows how information might escape, but the actual mechanics of how it gets out of a real astrophysical black hole remain unknown. This forces us to reevaluate what a black hole is. Instead of being a fundamental object, it may be a thermodynamic phase, a coarse-grained description of many microscopic parts. In this view, concepts like locality and distance are emergent. They are the result of how quantum information is encoded and protected across different parts of the system. This suggests that the rules of general relativity are not the final word, but an effective description of an underlying quantum structure. Black holes may not be the places where information dies, but rather the environments that force us to confront the limits of our current theories. The paradox they create is our most direct lead toward understanding the quantum nature of gravity.